So, welcome again from my side. My name is Christian Stauch. I'm part of HYDAC group for roughly 16 years right now, maybe 17 in the meantime. And I'm in charge of e-mobility for HYDAC, so I take care about our product portfolio, about our projects when it comes to electrification of mobile machinery. And it's my pleasure today to guide you through that webinar, the first webinar in our series Forum E-Mobility. And I'm quite happy to have a lot of people on board. We have people from the US, we have people from Asia, we have people from Europe, so quite an interesting audience. And we want to talk about e-mobility. And e-mobility is, for us usually means e-mobility in mobile machinery, as for most of you, of course. So let's see what's the topics today and what's the idea of Forum E-Mobility. As I think most of you know, most of you feel and see that this year, especially 2024, when it comes to e-mobility, is not the most easy year we had so far. And I think a good chart to illustrate that, and maybe also a bit to explain that, is that so-called hype cycle. So some of you might have seen that hype cycle before. You see that, that kind of chart here, and it shows the visibility of a newly to market introduced technology over time. So usually it's called hype cycle. What you see here, there is a sharp peak in the very beginning of the curve. You see that right here. Here it's called the peak of inflated expectations. And this is where the hype actually is. And when we look into 2024, I think we all know that, we all see that we are maybe beyond this peak when it comes to visibility, of course. Because we have had very interesting shows. We have had a very interesting ramp-ups and series start and interest in e-mobility over the last 4 to 5 years, and we see some, let's say, slowing down of the acceleration, so to say, when it comes to e-mobility. So what we are coming back to that hype cycle, we're probably behind that peak, but we still don't know, are we in the so-called through of delusionment, or are we again on the slope of enlightenment? So let's hope for the best, but this is kind of the situation we are in right now, and this is kind of the situation we want to cope with, and of course we want to go this direction. And I'm going to show you how we can help or do that together in the next few slides. There is another thing when it comes to individual experiences that has quite the same curve. This is called the so-called Dunning-Kruger effect, and this is more about personal knowledge and confidence. And this is also, again, about new technologies, because everybody of us is kind of, when we started with e-mobility, we were kind of a beginner, and this shows confidence over knowledge. It could also be confidence over time, because we assume that knowledge is increasing over time, at least we hope so, everybody. And we see when we were a beginner, we had quite little knowledge and quite little confidence. And after starting working in e-mobility, most of us felt more confident. And then when it comes to practice, when we learn things, when things go wrong, typically confidence is dropping again. This is here. So this is a very similar curve to the hype cycle. And as with the hype cycle, also here, the goal is, of course, in the end, we all want to become experts in e-mobility. So I'm pretty sure there is some experts in e-mobility. Not all are experts in e-mobility, but everybody wants to, and everybody wants to go that direction. And this is what the Forum e-mobility is about. Not about being experts, but working together and see how to overcome that gaps and how to help each other to become more knowledgeable, and in the end, of course, some kind of an expert when it comes to developing new electric machines. So the goals of that Forum e-mobility is, of course, we kick off a dialogue. We want to go in dialogue with our customers, with our partners. We want to share experiences, mutually sharing experiences, and we want to also rely on already proven solutions. And of course, not everything is developed, because we are not at the right end of that chart. So we also want to work together to solve some of the challenges that arise along that way. And zooming out again a bit, looking into the market situation, of course, at the same time, we want to achieve that so-called plateau of productivity. So that left-hand side of the chart here is where we want to go, because this is when electrification, when e-mobility in our market really has become standard, when it's become profitable, and so on. So what we see on the way there, all of us see, is that electrification still is quite a time-consuming process when it comes to develop electric machines. we can not really expect a real quick return on invest. So it's kind of a marathon we have to go through. And we see, especially in our business, when it comes to mobile machinery, it's about economy of scale. So we're not automotive, we don't have that huge quantities. We have a high variety in our applications in different branches, and we need some economy of scale. And one key element for that will be standardization and modularization. So acquiring quantities, acquiring the same components over different applications in order to have better cost in the machines, and that in order to leverage the end customer interest in electric machines, because we need to close that gap, that price gap between electric machines and conventional machines if we want to reach that plateau of productivity. And this is what we want to work with you together, all of us. So coming to the Forum e-mobility, the Forum e-mobility is not only the series of webinars, but it's kind of a hybrid forum, a virtual forum in terms of that webinars, and also including in-person events. So some of you have joined that first in-person event last year, and there will be future in-person events, but of course in that scale we don't want to do that like every some month, but more or less in a cadence of 2 to 3 years. So if you stick with that Forum e-mobility mailings, then you will be informed about future webinars, you will be informed about in-person events and about what's going on and how to foster that community of e-mobility. And today we are looking into the very first webinar of that series. We asked some of the questions. I said before we want to go into a dialogue, so we asked some interest questions up front and ask what is the topics that you are most interested in, and just to show here the categories, of course, as one might expect when it comes to electrification, electric drive technology was the topic that most of the people have been interested in, followed by battery systems. But, and that's really important, especially for our concept, it's also about practical examples and applications. So when it comes to these Forum e-mobility, one sub-headline of all that activities here is turning theory into practice. So it is really about practical examples and applications. It is of course about energy efficiency in work functions, but also in other functions. Functional safety is always a topic, now added with electrical safety, and that's also something that I'm going to refer to in this webinar, at least a bit. We have hydrogen in the area of zero emission machines, of course, playing some important role when it comes to larger machines. Thermal management is relevant for all of our machines, of course. We have the topic of software and systems integration, and the charging infrastructure as an enabler for e-mobility is something that is somehow interesting for a lot of you. And we're trying to cover the most relevant parts of that: electric drive technology, battery systems, practical examples in this first webinar. But of course, we only have 2 hours of time, so we cannot cover all the topics here. So expect a series of webinars to be followed, and we will also go into dialogue to find out what would be the most interesting parts for the upcoming webinars and so on. And dialogue is a really important word. I have been saying that quite often, and I will say that sometimes more, because I think that is what should be part of that series. So today the first webinar will be about systems architecture. It's called Beyond the Systems Architecture Black Box, and especially practical approaches to electric mobile machine engineering. It's about sharing experience that has been acquired so far, not being experts, but being somebody who's working on their knowledge when it comes to electric machines. And we want to keep up the dialogue also throughout this webinar. So please use your browser tabs, mobile phones to join Slido. You can do that right away, even though there is no actual question right now, because we will have Q&A, also the questions and answers in the end of that webinar based on Slido. So you can put your questions into the Slido Q&A section, and we will go through that questions in the end of the webinar. And throughout the presentation, we will have some questions, some votings, some open questions where you can also put your opinion. And as we also have some HYDAC participants in here for the colleagues here, please, for you, don't use that Slido because we want to use the Slido, of course, to give some kind of a market impression. We want to share the results of that Slido with all the participants afterwards so that everybody's getting a clear market impression. And if we have too much HYDAC attendees inside that picture, that would maybe not so good of a market representation. So HYDAC colleagues, please don't use Slido. It's just for external participants. Thank you. Okay, so let's start with the webinar. So usually when it comes to electric machines, everything starts with a product manager who is coming around and asking for some minor things like of course we want to have an electric machine. We want to have the machine to have the same performance as the conventional machine, of course, because it's about customer acceptance. Customer acceptance also means the runtime should be 8 hours because the diesel machine is running 8 hours. It should be never more expensive than a conventional one. And of course, we need to have it fast because there is a trade show. There is some important show over the next month, and some competitors are showing things. So it needs to be quick, it needs to be good, and it needs to be, in the best case, better than the conventional one. So this is putting a lot of challenges to machine development, machine engineering. And this is a point where we want to, let's say, do a test run, where we want to start with our first Slido, asking an open question. So the question here is, what is your challenges in the what is your biggest challenges in the development of electric vehicles? So please take a few seconds, log into Slido, use the passcode. You see everything here in the left-hand part of the slide, and bring in your ideas, your opinions. Give us an idea of what is your biggest challenge when it comes to electrification. Aus. So we have 4 participants typing, so it takes, usually for the first questions, it takes some time until everybody's ready to go. But we see some words are dropping in. Of course, this is something that's not surprising. It's about costs. It's product sizing. We see time to market. We see performance level of power electronics, so obviously about functional safety. We have long payback time. That's what I meant in the beginning. That's something that we have a marathon and not a sprint. Duty cycles, which I would interpret also as not available mission profiles of the machine because we don't need it. That's for the conventional machines. Power capacity might be related to battery sizes. So we still have people typing. Efficiency, of course, efficiency is something that is really important when it comes to cost in the end, because efficiency determines battery size and battery size determines cost. And we also see reliability, which I think is quite an interesting point, because there is a lot of new components, there is a lot of complexity, interaction, noise levels. Durability is also an interesting part. So the weight of the system, we see that in some weight critical applications, the battery sizes really become a challenge. And also a very interesting part from my point of view is customer value. So that's what we're facing today, that we only need to find end customers, so to say, that really want to buy the machine, and not only for funding reasons, but really for increased value and increased productivity reasons, of course. Customer acceptance is quite a similar category. High voltage components. Okay, safety is something that is repeatedly mentioned. That's why it's becoming bigger and bigger. Certification is something that is some of the same type. So, as I said in the beginning, we are going to collect all that information and of course share that among all the participants, that all of you get some kind of a, maybe not really representative in a scientific sense, but somehow representative market view with that answers. So thanks a lot for your participation and for your activity in that Slido. We're gonna have some more of that later on. Okay, so all of these, or a lot of these challenges is something that we have been discussing about before with customers, we have been seeing before. So we see, let's say, a leading topic when it comes to electric machines is complexity in new stuff, complexity in choosing the right systems architecture, in solving the conflicts of efficiency, cost, and performance. We found that a lot. We found efficiency, we found cost and customer acceptance. It's sizing. We also found sizing in the answers, having the right sizing of the components. It's getting things to work together. Even though we have a bunch of components, we have to make them to work together. That's something we're going to address later on. It's about testing, and it's about also commissioning new systems. It's about electrical safety. We had a lot of safety-related answers here. So this is what we think might be challenges from our point of view and what we want to address in this webinar today. And usually when it comes to systems engineering, when it comes to complexity, we're well used to use the V-model-based systems engineering process, and that's something we want to use kind of as kind of a guiding thread through that webinar today. So we're going to go through different stations in that V-model and always have a spotlight on some practical aspects. That's something that is really important to us to have that. That's why it's called theory into practice. We're going to have some tipping points here. You're going to find that label once in a while during the presentations to have some tips along the V-model when it comes to practical issues. So we're starting with systems topology. And for systems topology, I have a colleague with me. So Marcus Pfeiffer is going to present the first part of that system. Marcus, please come here, introduce yourself to the audience.
Hello, my name is Marcus Pfeiffer. I'm with HYDAC since almost 20 years, and I'm responsible in the team of e-mobility for topics like efficiency, hydraulics, and because I have an engineering background in customer machines, I also support on the application side.
Okay, so Marcus is going to show the first topic about system topology.
Thank you. If we talk about system topology, it's not always from the beginning clear in which direction to move or what to do, because we have differing applications with also in the same applications maybe some complete different requirements, because the machines are used in a very universal way. So we need to have solutions which are kind of flexible, that you do not every time reinvent the wheel. If we come to, for example, the topic which way to go, is also a question of the machine functions, because they also have part-wise very differing requirements. Like for example, you can have a machine where you have a ground drive system. That could be a hydraulic drive, but it also can be an electromechanical drive, no hydraulics in there anymore. It could be a winch drive, a motor drive, that means for example like an auxiliary attachment like a sweeper or something like that. It could be a steering unit you have to supply with hydraulics or electromechanics. Then you have swing drives like on an excavator or on a crane application. You have various kind of auxiliary functions. You even do not know what is maybe attached to the machine, so you need a very high flexibility there. You have linear working functions like cylinders on the implements. And of course you have ordinary power packs you somehow want to install in the machine. If we come, for example, to that topic, which direction to move, we also need to have a better picture what technologies are available and what are the advantages and disadvantages. So on one hand side, we talk typically, if we talk, for example, about implement controls, about the standard central electrohydraulics, which is typically a classic throttle control with integration of losses we do not want to have, we maybe have to get rid of if we have electrical machine. The other topic then is if you want to have a more efficient solution, maybe distributed solutions are the best for various functions. And the big advantage there is that you can keep the advantages of a hydraulic system. That means, for example, the power density and everything in that unit, but still have, I say, a higher efficiency, because you really have the function only, or you only have the supply unit on the function where it's operated. A third way to do it, of course, is in direction of electromechanics, like on smaller machines or even a little bit bigger machines. You meanwhile find, for example, that the ground drive system is completely electromechanic, but you still also find electrohydraulics. But also you see it more and more that in various applications it comes up to make the linear functions electromechanics, and I will say a little bit more about this in the next slide and show a little bit what are the advantages and disadvantages. And you have to understand them, because otherwise you maybe make the wrong choice in your application. And that's what we see in our daily work, that sometimes somebody jumps on something because he heard the rumors, but he did not make up his picture in a clear way to have a feeling what does he really need. That means if you take a look in the different functions or the different solutions for the functions, if we go in direction of a central hydraulic, you typically have a motor system where you have, I say, where you have, for example, a motor system with an inverter, a control unit. To the motor, typically you have attached a pump. It could be, I say, a complete power pack like you see right here. Then you have your throttle valve to make the operation of the individual functions. And of course, because I don't have the space on this slide, I only showed now one cylinder function, but it could be up to 10 functions, for example, being supplied by this one individual pump. If we come to distributed electrohydraulics, they usually are dedicated to one individual function, with the advantage that you all have everything going on directly on site. That means on board of that actuator unit. Therefore, you have very short paths, and you can generate a quite, I say, efficient hydraulic system if you need it, even in closed loop. So this could be an advantage if you need a certain high efficient solution, but you even could go one step further if you say, okay, I take, for instance, an electromechanic actuator, which is, if you make the right layout, the most efficient you can find in the applications, but it also has some drawbacks. It gets quite bulky if you need, for instance, high forces and stuff like that, so hydraulics is much better. And the other thing is, if you have, for example, electromechanic actuator, you always need for each actuator an individual motor. That means you maybe have to install on the machine multiple times the power you need on the machine. That is a little bit more easier, or it goes better if you go in direction, for instance, of a central hydraulic. So you always have to make the choice, okay, what do you really want? Is it about, for example, short time to realize the project, minimum technical risk and effort, or do you need, I say, a flexibility and scalability, or you have certain special assembly requirements? That means, for example, in your workshop, you want to stay with the procedure like that you know. You cannot, for example, change too much in the line. And then maybe also on the field service, you want to provide that the people working with the stuff know what they are doing, and that you do not start by Adam and Eve. Then it could be that maybe electrohydraulics is the best solution, and that's what you very often also find if somebody is electrifying a machine. They just exchange the diesel, leave everything like it was before. It's an easy task to move forward, but maybe it's not the most efficient. But of course, if you move in that direction, you go a step further and then also make investigations, for instance, what could be optimized, and out of, I say, that you then see what has to be done. With the distributed hydraulics, you have, of course, the possibility that you keep the power density of the hydraulic cylinders. You even could say you take a unit where the cylinder is separate in the machine and the power pack is sitting somewhere else. So you can keep the same environment like in the existing classic central hydraulics. And of course you can do it on multiple functions, because you can make a shift that you say you supply from that one pump, maybe various actuators. This is also not possible on an electromechanic actuator, so you need to have, I say, for each unit an individual motor. If we now go, for example, in the application, or which way should we go, a very important thing is that we have a feeling, for example, what is the use case and how is the machine operated. And very often you even cannot relate this to the individual machine, because you can have a machine which is maybe one time used as an excavator, the next time more like a crane function, and then you get complete different load cycles. Like for example in this application, and we stick with to this, we have like a material handler machine which is handling wood. And here, of course, you have, I say, if you have a throttle control, some losses in the system, which are shown right here. And you can see, for example, that you have quite high throttling losses in the boom system when you do your load cycles. So, of course, it is interesting to say, how can I get these losses down? Do we lower the pressure drop over the flow path? We looked into it. Okay, you can do a little bit about it, but that's not the major issue. The major issue is that we have to throttle, I say, the pressure down on that function over the valve. And if you have cases like this, the easiest thing to do is that you split up the circuits and put it maybe on a separate pump, so you can really operate it on the dedicated pressure level. And so you take out all these losses. And these kind of things, they are easily to establish, because all the control system around it keeps less or more the same. You have a classic, I say, maybe load sense control. You still have, I say, one electric motor which is doing a variable speed drive of the whole system, and the pumps are adjusting automatically to the LS requirements. But by doing this, you can gain, I say, efficiency levels of 15 to maybe 30%. So it's an easy task to do, and of course you should try to bring it in. So that means, for example, the improve affected individual functions we take out and put maybe on a separate pump, and keep all the other functions in a conventional environment, maybe even with the same valve which has been used before. So it is a known technology for the OEM and very easy to establish, for instance, in the machine, and not a 10-year development. If we come to the next point, and that is also very important, it's not only about efficiency, it's also that you have, I say, the right strategy in operating of your functions, that you can make a proper design, for example, of the motor and the whole drive system. So it's very important to analyze the load cycles here, for example, with that load share analysis chart you see right here, that you check how often is the system in standby, how often do I operate, for instance, in somewhere a middle range or maybe in the peak level. And what we could see here in this area is, or in this machine, that for that dedicated use case, they were very often in standby mode, and I say really peak demand only was very seldom in this small little black pie piece you see right here. So we easily came to the topic that we said, okay, why don't we make the layout not to a peak demand like you typically do it in a diesel engine? And that's very often done wrong in the application, that people just take the values they have from a diesel and transfer it to electrical motor. But for example, in this case, if you would do this, you would waste money. The motor would be too big and too expensive. So it's useful here to say, hey, I scale it down a little bit to the average, and for the peak demand, I do a certain adaptation or maybe boosting of the function, so you can work with a smaller motor. How do we do this? There are two possibilities, or various others too, additionally, that for example, if you keep it simple on smaller machines, you just take a constant pump, and instead of one constant pump, you take two. And depending on, for example, the requirements of the electric motor, you add, I say, both pumps to the drive system or only one pump. So you can influence the torque, and therefore, for example, can avoid an derating, for example, on the electric motor side. And if you need it more, I say, in a full scale, you can go in direction of a full torque adaptation by adding a variable displacement pump, where you really can do individual settings like you need it on the machine, and therefore you very seldom go in derating situations, maybe never with the motor, and you can keep the drive system quite small, and that's, like I mentioned before, has a strong effect on the cost, size, and the weight. So referring to this, what I just showed, and similar what Christian asked before, we also have a little Slido questionnaire here, and what I would like to know now from you is, for example, which of these topics you see right here are the three most interesting or important for your applications. So I would ask you now to select 3 and not more out of this. Again, it's not for the HYDAC guys, it's for the external, the customer guys, to really make this selection, and let's go for it. And you maybe have 1-2 minutes time, and then we go ahead. You can see that a lot of things are the same, but now they're moving a little bit. So scalability and easy integration is a very important point. Needs to fit in existing mechanical framework. Improved efficiency is quite important. It shows me, for example, that improved efficiency is maybe the top runner together with the scalability and easy integration. That's also less or more what we see in our daily applications, that this is really important. Okay, I think it's less or more settled in the stable way, so we don't have to dig deeper into it. But it's good to get this picture because we also will refer later on to that what we just investigated now here on the Slido. Of course, if you did not vote, you can proceed. But I think it shows clearly that efficiency and scalability and easy integration is a very important topic for you guys.
It's quite an interesting result actually, because of course everybody expected efficiency to be the top number one, but that we have this head-to-head race with scalability and easy integration is something that somehow surprises me, that is really heads up with that efficiency thing.
Yeah, so we have not seen it so much in the applications for them so far. I will now move forward and give it back to Christian, and we see us later on other topics. Thank you.
Thank you, Marcus. Okay, so we have been talking about systems topology so far, and of course the next step when we go along the V model, once we have determined a systems topology probably, which is of course highly dependent on the application, once we have the first kind of systems architecture, we want to look into the components. And we saw it also in the poll in the very beginning, that sizing of components, right sizing of components is of course a matter of weight, it's a matter of space, it's a matter of cost. So this is something that has some relevance, and that's why we want to also discuss about that. So when it comes to component sizing, of course, the question is where to begin, because we have a lot of new components that haven't been there in a machine before, so where to begin with. Natural choice would be probably the voltage of the system, of course, because that's determining more or less everything in the vehicle. It is probably the battery, the most cost, space, and weight driving component in the vehicle, or is it the drives? Because the drives are actually doing the work or doing the driving. That's what the vehicle is there for. So start from the actual application. Well, the question is, and then that section is called component sizing from a systems perspective. It's not that easy to just start with something and then go step by step in a linear way from one component to another, have a sizing for everything and go to the machine, because everything is connected to everything. So we're talking about a system, and usually everything is influenced by the other things. So we kind of need to do that iteratively. And of course, we don't want to do it iteratively in terms of prototypes, but we need to do it iteratively in a pragmatic way. And there is some aspects of that pragmatic way we want to show right now. So let's start with the voltage, because of course it's the most natural choice. The most asked question when you start with a new vehicle, what kind of voltage do I need? And I'm trying to use a bit oversimplification to keep it practical, but of course I'm going to tell you why. So the simplified answer is 500. But 500 what? Of course it's not 500 volts, which is the answer to what is the right voltage, but it's rather having a look to 500 amps. Because 500 amps somehow brings a, let's say, a natural limit. So we have a chart here. We see on on the x-axis of this chart, we see the continuous power that is used in the vehicle, and on the y-axis, which is for illustration purposes, it's actually a logarithmic scale, so please don't be too much confused about the distances between the numbers, but it's roughly from 0 to 1000 volts, and we have up to 300 amps here. And the 500 amps line is the line we say as a rule of thumb that should not be crossed if there's not important reasons to do so. And it's quite simple. Why? Because if you cross that 500 amps lines and you are in that section below that line, it is typically cost driving. The component availability is dramatically decreasing because it's really huge machines. It's not common in automotive or in light transport applications. So there is less available components, usually less competition means higher prices. So it's cost driving. The cable cross sections get dramatically higher. And when it comes to cables, it's about copper. Copper prices, I think everybody has seen the development of the copper prices. It's going to be about connectors, especially in the higher powers and high voltage. We use a lot of connectors also for electrical safety, and this is also cost-driving elements. And of course, the power distribution unit, the switching elements, the fuses, and everything will be more expensive, and everything is scaling with the current. So 500 amps is, from what we learn in the applications, quite a reasonable border that should not be crossed. And when we have small machines, let's say up to 20 kilowatt continuous, we end up with a 48 volt system being probably the best choice for that kind of vehicles. Because 48 volt has another advantage, it's safety, extra low voltage. So there is reduced measures. I on purpose don't say there is no measures, but there is reduced measures when it comes to electrical safety. We're going to see that afterwards, that it's also relevant for 48 volt. And especially when it comes to training of your people, of the staff. Because the world, also the electric world, doesn't obviously end at 20 kilowatt. There is another level, which is also quite common in the market so far, which is the 96 volt level, roughly in battery voltage ranges between 70 something, 80 volts, up to 120 volt, and 120 volt also is the threshold for so-called functional extra low voltage, which again makes some difference when it comes to electrical safety. But once we cross that line, we are in a mobile application, in an automotive sense, in a high voltage world. And that does mean there is two typical voltage levels. The first one is 400 volts, coming from early adopting in the automotive industry, and also in a lot of industries that have been electrifying quite early, such as municipal vehicles, for example, where we see a lot of distribution of 400 volt systems, typically in the range between 270, maybe 250, up to 540 volts battery voltage range. And this is feasible up to 150 kilowatt continuous. And when you think about machines that have 150 kilowatt continuous power, then you see that you could theoretically cover a lot of applications that might make sense to be electrified in the first place with that kind of voltage. Nevertheless, we see a strong trend towards 800 volts. Not only in automotive industry, who is step by step going to 800 volts, but also and especially in off-highway, because there has been increase in available components after the last years. There is, when you have the same power and you double the voltage, you halve the current, and then again, remember the current is a cost driver, so the 800 volts might be something that is considered in the majority of the high voltage applications that we see in today's new development projects or NPI projects. But nevertheless, this is the, so to say, this is the HYDAC view that we have in the market. Of course, we're also interested in your view again. So another Slido, which is asking the questions, which voltage levels are relevant in your machine portfolio? And this means are relevant in the machines you have electric today, probably, and also what you're looking into in the future. So please take a minute or two and give us some answer on that. And again, multiple answers are okay, because of course some of you have fleets that have covered different voltage levels. So step by step approaching the 30 participants, maybe a bit more than 30 participants, but that's usually the number of really active participants in the polls here. And there's also a surprise in these results, at least for me, because I said it before, 400 volts is something that has been early adopted and that is well adopted in the high voltage area in the market, but it's still the number one answer in this poll. And that's something actually I didn't expect. So when you look into market data, the electric machines you see in the market today, a huge majority is 48 volts and then maybe also 96 volts, and then high voltage is still the minority, but it clearly gives us a trend in what direction development is going in the market with electric machine development. So we have 400 volt in the first place, but close to that also 800 volt. High voltage is obviously really interesting to that. So in the further course of this webinar, we're going to have examples both from low voltage and from high voltage. So we're going to see some of both. Okay, now 800 volt is catching up. I think the poll is still open, but let's go a bit further. Oh, 800 volt has taken the lead right now. Okay, I've been talking about that 500 amps border, or that 500 amps line that we do not want to cross if we don't really have urgent or important reasons to do so. So one question about that 500 amps is, when I talk about 500 amps, is it the AC 500 amps or is it DC current 500 amps? So AC current would mean the current between the inverter and the electric motor, typically the current that you use for sizing of the inverter, for sizing of the motor, or is it rather 500 amps DC, which is the current that you use for sizing the battery, you use for sizing the PDUs, the fuses, and so on. So I've not been talking about that before. And then this is again a bit of an oversimplification and a rule of thumb, but I think it's quite important when it comes to having doing the first shots in new machine engineering. And the answer to that basically is it's both. So it's 500 amps DC or AC, doesn't really matter when it comes to maximum current sizing. And I'm just going to show you why. This is a webinar, so a bit of equations we need to go through. So what we see here is a power balance at the inverter. So under the red is on the DC part of the inverter, we see the incoming power, and we want to balance that with the power going out of the inverter. So therefore we have to take the efficiency of the inverter into account, but electric power usually is voltage times current, so quite easy at the DC part. There is a bit more complicated equation at the AC part, which takes into account the power factor, the so-called cosine phi power factor. We have the AC current, we have the AC voltage, and we have that, because we have a three-phase system, we have that factor of square root of 3. And we can now do some simplification, because we know that once we are in a operating point where maximum current sizing is relevant, then usually we use the full voltage available, so we can replace the AC voltage, and we can do some further simplification, and we end up with an expression that is, in most of the cases, in nearly all of the cases, close to 1. And this means that IDC is roughly the same as IAC. So when it comes to current sizing, it's both okay. When it comes to 500 amps, respecting that 500 amps, it's both okay to take that for DC and for AC. So again, that is a bit of juggling with equations, but in the end, it's about theory into practice, giving us a rule of thumb where to go when it comes to not only battery sizing, but also drive sizing. And this is something we want to have a closer look into right now. So how to size your drives. And we want to do that in one practical example and really in a pragmatic way. So let's see what's the steps here. The very first step, usually talking about pragmatic ways, is to guesstimate. Right? We have an idea of our application. We maybe have also some data. Let's say in this case, very simple data. We have a system that has a hydraulics drive probably with 250 bars, 15 liters per minute. So we can roughly estimate it's 7.5 kilowatt. So let's look for a drive, a motor that has 7.5 kilowatt. You can find something like this. We see it's not exactly 7.5, it's 10 kilowatts, so it's a bit oversized, but we're talking about the very first step, we're talking about guesstimating, so why not go ahead with that? Then, in the this of course means that it's only datasheet characteristical points, but we need to look into the application. Load cycle analysis is really let's say, a big word. We have been seeing in the beginning also in the challenges, we don't always have load cycles available. Sometimes we only have operating points we know from the diesel engine. For example, we could also say we have a continuous operating point here with 85 bars, which is kind of an average value here. And we have a peak operating point with 245, 250 bars, close to the maximum that the system can achieve. And with that 2 operating points, we can go back to the data sheet and we find out, oh, okay, that 85 bars is really the average. So the continuous 10 kilowatt of the motor might be way too big, because 85 bars is a third of the 250, so we're roughly talking about 2.5 kilowatts. So why choosing that 10 kilowatt motor? We should take a closer look. The first thing is we're talking about a hydraulic drive, and we see in the data sheet that the nominal power is at 3,750 RPMs. So usually in hydraulic drives we often have lower pump speed. So for example, we also would have a lower power at a lower pump speed. At the same time, it's also about cooling. In this case, 7.5, 10 kilowatts, we're talking about a low voltage system typically. Remember, below 20 kilowatts, we easily can go with 48 volt systems. So we're talking a lot about air-cooled systems, and then we also need some airflow for cooling and so on. And that's the reason why we want to have a closer look to the motor dimensioning. So a very simple, easy thing to do. Everybody can do that today, and we also have our tools to do that is simulate. For example, here we have a MATLAB-based, a web-based motor simulator. I'm going to show an impression of how the engineers, how our sales engineers, or our technical sales people, or support people supporting customers in the projects are using that. So we can select the motor we selected in the data sheets. We can also select the inverter that is okay for that motor. The simulation data is available, and then we have to do some adoptions. That we are more dynamic as a pure data sheet. For example, we adopt the DC link voltage to the end of discharge voltage, because we also want to have performance at the empty battery, and we adapt the air rate. And what we get here is a very special plot that relates to the operating points that we have been determining before when we did our load cycle analysis. We can also calculate that points explicitly. For example, at 12 Newton meters torque here would be the 85 bars we have seen before, and at 34 Newton meters would be the 245, 250 Newton meters. So we can use now that data that is created here, we can export that, we can take that for further calculations and so on. And we also can go back to the full machine plot, to the performance plot, and also extract that data and use that for further analysis in whatever tools we want to use with that. Okay, so once we have that export, we can actually look into the motor curves and find out if our operating points are still working under that special operating conditions, like with lower battery voltage, with lower airflow rate, and so on. And what we can see here is this is now a special motor curve that has been created by that tool, especially for that situations. And we see 2 operating points. The one is the continuous operating point, the blue one here. And we see when it comes to current, which is determining the motor size in the end, it's below that. The operating point is below that continuous operation line. And we also see that the peak current is quite a bit below the peak curve of the motor. So seems quite good. Seems that we have no problem, but we also are not heavily oversized, because here we see the continuous operation is pretty close to that line. But what about that peak operation? We did quite a simple load cycle analysis. We just had a look on where is the peaks, but we don't know how long the peaks are. So this typically is a peak operation point, but we're talking not about seconds. Sometimes we're talking also about minutes of operation in that 250 bars. So how do we get an idea of that? Of course, we could do a full scope motor simulation with every boundary condition and so on. But at some point when it comes to engineering, there's also it will be also about testing, because there is a lot of boundary conditions that should be taken into account. And from our point of view, it might make sense to do some testing. So in this case, we have our systems test stand used for that. So the test stand here is consisting really of a mobile-like system. We have batteries, we have a power distribution unit, we have inverters in there, and we have, you see the power distribution unit, you have the drive inverter, and here you see a back-to-back configuration of 2 motors. We can use one motor in speed mode, one in torque mode, and really do some testing about that. And what we're testing here right now is the thermal behavior in these operating points that we have been identifying before with that simulation program and with that gases we did. So thermal measurements usually take some minutes. Of course, there is a high thermal capacity in that motor, so we did some tests running in that. We did a data acquisition with a handheld measurement device, and here is an accelerated video of that data acquisition, and we see a typical temperature behavior. And in addition to that measurements, what we like to do from time to time is also to get really an impression of the heat distribution. Not in the motor, you see that's quite homogeneous, but also how is the heat how is the heat transferred to the system? So through the mechanical adaptation, for example, we have some heat transfer to the flange, we have some heat transfer to the cables, just to get an understanding of the motor situation in a machine. And this is again about practical things to understand how to mount a motor in a machine to make sure, on the one hand, to get a good deheating of the motor, and on the other hand, not to heat too many parts in proximity of the motor. And also we did some other tests, like, for example, for the peak power demand, and we tested for how long can we have that peak power demand here. The result here, for example, was we could run even with a preheated motor, so a motor that has been running continuous before, we can run with that peak operating point up to 6 minutes. So obviously it's not a peak, it's some kind of S9 motor profile that we can cover with that. And in the end, of course, this all brings us to a point where we say we have quite confidence that it works. It might have looked like a bit of over-them or a lot of oversizing in the first place, but in the end you have to respect the boundary conditions. You can do that best in the vehicle because the boundary conditions in the vehicle might also be very special. And somebody who really knows that from application experience is Marcus. So Marcus, there's another example that you can tell us a bit about your experience when you worked with air-cooled motors in low voltage applications.
So I'm back. It's not so much that we now split up the presentation. It's also because this is a case where I said we ran into some problems in a dedicated application. Then my colleagues asked me, Marcus, we have some problems here with maybe heating up of the air-cooled motor. So we had to find a solution for it, how to handle this. And I want to show a few slides and talk a little bit about, okay, what you have to look in when you go in direction of air cooling. Because like what Christian already mentioned, of course, air cooling is used if you have lower power requirements. And if you want for sure to have, I say, a cost-efficient or a non-costly solution in your application. But if you make it the wrong way, you maybe can have a lot of additional costs to solve maybe overheating and derating problems in the application. I do not show an application on a sailboat now, even if we are with motors in sailboats on the control side, but I say bigger sailboats. It's more about to make an introduction, what is important. And when you look on the sailboat here, it's like the sailboat is standing constant in one position on the mirror because there is nothing going on from the wind side. So what do air-cooled motors and sailboats have in common? Very simple. They both need a certain breeze, a certain decent breeze, if they want to perform on the best level. So that means you need a certain wind coming up for the sailboat, and you need a certain airstream on the electric motor. That means on the air-cooled motor, if you really want to operate it on a certain power level. So, for instance, when you look here, this is now an cut out of our specifications, and you can see that the requirement is 6 meters per second of airstream. If you now transfer this, I say, to a speed of a machine, if you have a machine which runs very slow, you never will get there. So it could maybe be an issue. So the question is also, is it feasible to keep the required theoretical airstream at all the times? For me, from my side, the clear answer, no. In some cases, or in a lot of cases, it is fulfilling the requirements if you have machines which run a little bit faster. But we also have applications where you cannot fulfill the requirements because maybe the design is done in a way, like we also saw on the questionnaire in Slido before, where one major point was to keep, I say, the framework in the existing machine. And that is also sometimes hindering to come up with the best drive solution. That means especially when you have like an air-cooled system, you maybe have to dump your motor in a corner on the machine in the frame where you really have no air stream coming by, and that's independent if the machine is running slow in its work or maybe fast, where you have a certain airstream maybe on the machine but not around the motor. And in this one specific situation, we detected early enough on the design of the machine because it was a no-go to make a big change on the housings of the machine. So we had to get everything in the framework which was existing. And unfortunately, the motors were sitting in a very, I say, isolated spot where you had the frame of the machine going around. So the airstream was not on a real good level. And or we thought about that this maybe will be the case. So what we did then is that we said, okay, we have our specialists on the cooling side who do a lot of simulation of airstreams for cooling systems. So why don't we need this expertise we have in-house to analyze what is the best airstream or maybe the perfect airstream if we want to integrate air-cooled motors in these kind of, I say, challenging applications. So we made an analysis of the existing design. And what we could see, you see it here in the left picture, is everything what is blue, there's almost no movement. That means the speed of the air is 0. So it's far below that what we just saw in the specification, what is required. And what you easily can see here, there where it's red, you have the highest speed going through. And it was very simple because the air which was going through the hood was exactly coming in at that spot and directly went the path of the lowest resistance in, out, boom. But with the effect that you have zones in the whole system which are not really very good handled from the thermal management. So we were using this simulation to then develop further strategies in how to improve the system. And the solution, or one of the solutions you can see on the right side, was then as an outcome that, for instance, we looked into, is it possible to get a certain airstream in a better way over the motor? By driving of the machine, it was impossible because there was not enough air coming in. So it was obvious, okay, we need an additional auxiliary fan to get the airstream over the motor. And what we did here to save cost, we used, for example, the fan of the existing hydraulic system, but instead of like on a typical cooler, soaking the air in through the cooling element and then out of the fan, we turned it around 180 degrees and put the fan on one side and opened the mechanical structure on the other side with bores and holes, so we could pull in the air from the other side under the hood over the motors and other affected components and push it out through the cooler. So we had the effect that we had cool air to cool down the motor, but still, I say, on a decent level, so we could operate the hydraulic cooler in a certain way. And the big benefit was that we had a much better cooling on the air-cooled system and could work on this application with the air-cooled motor without adding additional costs, because we use the fan drive which is existing for the cooling system. And that is important, because if you don't take this under consideration, you maybe add additional fan drives and whatever, and this will be additional cost. So we use very strong our expertise in simulation, not only on this topic, also on others, to have, I say, the best layout then for these kind of solutions. And of course, we use this also for individual support of the customers. Thank you. I will give it over to Christian, and we will see us later.
Thank you, Marcus. So just recapitalizing that again, or rethinking about that again, about the motor sizing, to give a summary of that. So what we did is we started with the very first guess, which seemed to be heavily oversized in the first place. But then we really took the application requirements into account, and this is clearly an application requirement. We have some mounting position, and we have to live with that because the vehicle doesn't allow us to mount the motor, let's say, on top of the cabin or something like that. And therefore, we need to really look into that conditions. We need to do some simulation, we need to do some testing, and we find out that the motor size isn't too bad, even though it seemed to be oversized in the first place. And this is really a lesson we learned, that we have to go behind the data sheets, we have to go one step further, and then really look into the thermal environments, and then find clever solutions that do not increase the cost. Of course, you could, for example, if you don't have air, you could use water cooling, but we're talking about a 48-volt application. We're talking about cost-sensitive applications. If you add water cooling to a 48-volt system, which is not really common there, then it is added cost again. So it might be, from an economical point of view, better to have a motor that seems to be oversized in the first place, but is perfectly suiting with the right setup of air cooling there. So yeah, just to sum up a practical example on that. Next step is to look into the battery. So again, we have a multi-step approach, but I don't want to go through that in that detail that we just did for the motor. Again, I want to do some oversimplification. I want to give you just a number, how to size a battery. The answer is 10. Of course, the answer is not 10 kilowatt hours again, as you can expect, but I again want to show you why I think 10 is a good number to start with when it comes to battery sizing. So basically battery sizing is about finding out how much energy do I need on the vehicle to operate it for a given time. And usually we have quite a good hint when it comes to the vehicle, because we have a conventional vehicle that is fulfilling the same functions. So if we draw a line at the functions, we know that the power, both for the electric vehicle, at least the average, but let's say the average power, both for the electric vehicle and for the conventional vehicle, must be the same when we're talking about the same application. When we look into the electric vehicle, let's start with an assumption of 4 hours that we want to work with that, and we have some overall efficiency in the drivetrain of 80%. For a conventional vehicle using a diesel engine, we have, when it comes to overall drive efficiency, we have a bit poorer efficiency, about 0.2 or 20% efficiency. And there's also one important number when it comes to calculating the power. That is the power density of diesel. It's stated here with 9.8 kilowatt hours per liter. And now we're again doing some balancing equations. And we see in the first example, we have the power, the average power that is used in the electric vehicle. It's the battery capacity over 4 hours. So the battery is meant to last 4 hours times the system's efficiency. In the conventional vehicle, we have the average power that we can derive from the fuel consumption. That's a value, even though we do not know emission profiles, most of us know at the end of the day how much fuel did we consume. So we have the average fuel consumptions of the vehicles, and that's a value we can use quite easily. And again, we have a point where we do some balancing, so we can put together those two equations, and we end up with a simple equation for a first shot of the battery capacity, which is actually the fuel consumption times 10 allows us to have a battery that's operating the very same application for 4 hours. Of course, as I said in the beginning, this is oversimplification, but I'm going to show you in a second why I think it totally makes sense to go with that. So just to double check, for example, let's assume you have a vehicle with an average fuel consumption of about 5 liters per hour, and you want to operate that vehicle for about 6 hours, then you would, as a first shot, end up with a battery capacity of 75 kilowatt hours, which does not sound too unreasonable in the first place, I think. And the reason why we want to do it that simply is I'm going to show you that further. There is more things to take into account than just the capacity. Of course, you need to think about the charging strategy. So it doesn't make sense to really size a battery to the last watt hour and then think about the charging strategy. Again, it's an iterative process. You need to think about modularity. We've been talking about customer acceptance, we've been talking about cost, so there might be different use cases for the same machine. Some of them might be double the capacity or double the uptime than the others need to have. So it's also about finding a battery system that is modular. And then we're talking of highway, we're talking about, let's say, moderate quantities. So usually it makes sense to look for available batteries. We can, let's say on a paper simulation, we can design every battery we like, but in the end, designing a totally new battery with all the certification and all the engineering effort that comes with that might be not really paying off in the end. So it might make sense, and it's again coming back to the very first picture I showed. It's about reaching a market situation where we have customer acceptance. We want to reach that plateau of productivity, and we have to find some economies of scale. So we need some standardization and modularization. Therefore, it makes sense to really look for something that's available in the first place. And then, of course, we need to check space, claim, and weight, which we have found out also in your answers is quite important for you. And then is the point to check the detailed specification. So usually it helps with starting with some rough estimate, and the rough estimate is 10 times the fuel consumption. This is the learning, the takeaway that we have seen in a lot of projects, that this very first guess isn't too bad, and then it's especially step 2 and step 3 that make us look into the right battery solutions. Okay, then just one more aspect, because I want to bring in that aspect because I learned over a lot of projects that when talking about the PDUs, the PDU, the power distribution unit, is something that is being discussed in a lot of projects too late. Then there is no time, there is no space left in the machine, and there is no budget left for a PDU. But at the same time, a PDU is determining a lot of things in an electric vehicle. It's unfortunately today also it's still a cost driver in the machines. It has some certain space claim in the machine, and it also, and I'm going to discuss it on a few examples, it's also about availability. So when it comes to cost, we see that there is some costly parts like contactors, like fuses, and highly individual solutions usually lead to high cost because you have low quantities, you have a lot of assembly in these kind of units, so it makes sense to have some kind of standardization and modularization. For example, to have a design that allows for different sizes of fuses, different sizes of contactors, and to really add that in a modular way. Space is a thing that really needs to be optimized when it comes to PDUs. But that's the point, it's not just the cabinet. When you do some space optimization, and we're talking about the magical 500 amps that we might see in the vehicles, there is some heat that is created not only in the motors and in the inverters, but also in the PDU. So for example, this is a picture of a thermal validation we did here for contactors, for the contact points, for the fuses and so on, because we are again in a low airflow situation, high currents, so you really have to do some design verification on that. And that's what I meant with there is no time left in the project. Usually you should take that time if you're not using a standard part. And also space optimization is using these nice kind of ATO fuses, but usually they are not really, at least from a datasheet point of view, qualified for these kind of applications. So for example, when it comes to battery short circuits, you really have to make sure that these space-saving fuses can cope battery short circuits, and this is usually done with some testing. So here also we conducted some tests with that fuses to really be sure that we can use them in power distribution units and save space in that way. And then talking about availability, we also had that in the answers to our challenge Slido in the beginning. Availability is an issue when it comes to electric vehicles. And here we have made the experience that poor quality in the PDU, when you have no time and so on, really leads to malfunction in operation, and maybe to also too late malfunctions. Like we have problems with freezing contactors, with moisture and freezing conditions, and contactors are freezing, and switch on is not possible again anymore. Or we have isolation faults due to bad cables. We have bad electric connections, which again brings heating problems. And we also have experience with interlock faults in some applications that then are causing the vehicle not to work anymore. So having a good design in the PDU, and also for cost saving, standardization, modularization, is quite important. And also, there is some points where I think we have been in an early design phase for these kind of things, so there's a lot of potential for optimization. This is what a typical low voltage PDU looks like. Usually you don't have connectors because there is no really good low voltage connectors with a price that is acceptable, so you use cable clamps, but this brings, of course, the problem that once you use cable clamps, you have to contact the cables inside the PDU. And usually you have to do that when you are in vehicle production, which is not really nice. So one idea we brought up over the last projects is to change the concept of contacting and to have these kind of board contacts on the outside side of the PDU. So you can mount the PDU to the vehicle and connect the cables, the inverter cables, the charger cables, the battery cables afterwards. So you don't have to open the PDU, you don't have to do a lot of complex assembly, you just have to contact the cables like you know it from low voltage inverters, typically from inverters, for example. And this is something that helps in the end to save space and probably also to save cost. So this is quite a new concept, and again, for us it's interesting to have some voice of customer here. So please, especially those of you who are working in 48 volt systems, give us a brief feedback of how relevant such a concept would be for you. So I'm happy that the other answers, except for not relevant, are also taking up a bit. Okay, so we're ending up with somewhere above 20 participants. So especially those who who are interested to learn more, who all even say, I'd love to test, please come back to us. You know how to contact us. Please come back to either your HYDAC contact or immediately to the organization of this event and let us know that you are interested in testing such a device. Thank you for that. Okay, so we've been talking not only about component sizing, but also about getting things to work together, about system complexity, and we want to go again a step further in the V model and have a look into systems architectures, into verification of that systems architecture and how things come together. So this is again, I say it the third time, an oversimplification, a very generic way of representing a systems architecture. On the right-hand side, you have the vehicle functions like hydraulics, like a ground drive, like a fan drive, and maybe auxiliary drives. We have a cooling system here, usually a passive cooling system, which means that you use liquid, which has a heat exchanger to air. We have a battery on the left-hand side that is supplying the energy. We have a PDU. We just learned about the PDU. We have some energy distribution part. We have an onboard charger, a DC-DC converter. We have the machine ECU as central control part of the machine. We have some HMIs, some telematics unit, and probably also to have some battery to show just the full scope of possible complexity in such a vehicle. But we said we want to make it more practical. Okay, so this is something I just missed. So sorry for that. One more Slido question. So usually we have a lot of these components that are talking to each other, and as we know it for today, most of them or nearly all of them are using CAN bus. We have some LIN bus components when it comes to thermal management, but mostly it is CAN bus. Nevertheless, especially in automotive, we see some certain trends towards Ethernet, and it would be interesting to see what is the opinion in the off-highway world. So what you as machine designers do you think about Ethernet-based communication in your applications? Is that something that you expect in a short time? Is that something that you think will never really be relevant? Give us your insight on it. And of course, if none of the answers is really suitable, you can also use the ideas section in Slido to bring in your own opinion. Okay, so we're approaching the 30 participants right now. So what we see here is it will become relevant as a standard communication, but of course alongside CAN. This is also something that is not too much surprising because we have a lot of distribution of CAN in the systems, and we don't also think that it is being replaced in a short time. But it becomes relevant, which is also again relevant for us as a supplier working on new components to consider that kind of requirements in that new developments. Thank you for that. So coming back again to more practical systems architectures, I cooked it down a bit to a high voltage architecture we see here, where we have only one hydraulic drive. We have some cooling for the drive. We have a machine ECU, a vehicle control unit, so to say, a high voltage PDU, a high voltage battery, an onboard charger, and a DC-DC converter. And this is not something I created just for the webinar, but it's really a system that we have in a live setup here. So you see that here we have some systems engineer standing closely to that and praying that everything is working well with that high voltage system. And what we're doing here, you see that in this kind of test setup, what we're doing here is we're trying to have a system setup before going to the vehicle. And this is not, as you saw in the first video, this is not a test stand, but this is really a mock-up, a first functional prototype to get things work together. So here we need more flexibility, but also we have the possibility to test things together. So again, as a reminder, this was the systems architecture. And one of the problems we're facing here right now is when we look into the main components, each of these components have their own states. So for example, looking into the battery has states that you would expect, like drive and charge, but there is also fast charge, there is DC-DC operation, there is an init state, there is an error state, and we have the same for most of the components also. When looking into the inverter, you have about 10 states, the onboard charger has about 10 different states, and at least the DC-DC converter only has 5, which is, from a systems integrator's point of view, maybe quite okay. And when you look into the procedures, for example, working, it starts with activating the key switch, but there's a lot of steps that need to be taken. And between those steps, this is the systems perspective, coming back to the component perspective again, between those steps, the state machine of the systems has to run through different states. So you have like a multi-layer state machine, which really makes things complicated in the first place. It's not that it's not manageable, it's more complicated than it's complex, because you always can find a solution to it, but it requires a lot of testing, it requires a lot of good knowledge of the components, and especially it requires control. You need to be in control. So you can imagine when you think of a systems architecture, a conventional systems architecture where you have a so-called K15, Klemme 15 in Deutsch, where you just have the ignition key and everything is starting up, that won't work with such complex startup procedures as we have it right here. Because there will be collisions on the CAN bus, there will be messages that will not be received and will be expected and so on, and everything is going into error mode. So what we're doing here, just to give an example of such a vehicle pin out, is we're controlling K15. So every high voltage component has its own K15, and we use the central ECU to control every K15, and we wake up the component when the vehicle state machine is ready to bring that component in that situation. So keep control of your wake-up system. This is what we're doing in order to somehow reduce the complexity. And now we can see a typical upstart procedure right here. So Yannick is activating the system right now, and we see the control unit is live, the interlock is tested, isolation is tested, the battery is live, DC-DC converter is live, and the drivetrain is ready to be used. I didn't, on purpose, didn't want to slow it down because upstart procedures is of course quite critical. When you sit into the vehicle, you don't want to wait 2 minutes until high voltage is ready. It's really real-time situation that you see right here, and you're within seconds, you can control the motor speed for your application. And this is, again, to sum up, this is what we're doing here, setting up these kind of test setups before going to the vehicle in order to solve all these kind of problems that come along with that upstart procedures and so on, to avoid having a lot of troubleshooting in machine prototypes. Okay, so one more question for Slido is, how do you estimate the increase in software and systems engineering effort for electric machines compared to conventional machines? So when you have a certain effort for a conventional machine, how much more effort do you need to put into an electric machine? And there is a rating in a range from 1 to 5. So 1 means the same effort, and 5 means 5 times the effort. So please give us your ideas on that. I think I can show the answers up front. So I hope I didn't do too much framing with explaining the complexity up front, because we see the 5 is clearly leading. And this is also, to me, it's on the one hand quite interesting. On the other hand, it's kind of a confirming result, because our own estimations actually said that we have a factor 3 to 4 times the effort when it comes to systems engineering for an electric machine. And this is basically what the average score of this chart is also saying, that we are in 3.9, so nearly 4 times the effort that we have in there. And that again makes it necessary to have such kind of system setups, to have mock-ups to really test things in a system setup. And also what we're doing there is about reducing complexity, or not only reducing complexity, but also helping with time to market, is to again do standardization and modularization. So especially when it comes to the communication protocols of the components, this is something that is repeating from project to project again. So this is something that clearly can be standardized in such component drivers. And of course, there is standard functional packages like a ground drive, like a thermal management system. But nevertheless, you have seen it in the complexity of the state machines of the components, and you have seen it in the upstart procedures of the vehicle, that from vehicle to vehicle there might be a certain adaptation work. So it's important to have your building blocks to work with, but it's always again necessary to do some engineering work when it comes to first setting up the system. So let's sum up some takeaways when it comes to this kind of system integration, especially when it comes to setting up first prototypes. You should start with a functional specification, because that helps you getting the procedures right and getting an understanding of what you expect from the components. Then you should know the state machines of the components, because that would not bring any behavior that you would not expect. You should know the CAN protocols, when to send which messages. And remember that K15 control I've been showing in the pinout. It's about thoroughly design both hard and software architecture to keep in control, to avoid situations where you have collisions in states and you don't really have the possibility to do something about that. And in the end, it's about testing. And not only because testing, because testing is validation, but it's also because we have components where probably something in the documentation still is wrong, something is missing, because there is a lot of new components to the market. So you always have to expect the unexpected when it comes to setting up a new high voltage system. This is what we want to hear as a learning, flexibility and testing, as a learning that we had over the last few years. Flexibility and testing in the beginning saves a lot of prototype time in the further course of the project. Okay, So then let's have a brief look into electrical safety. So that's also one of the points that has been mentioned as interesting. So when it comes to electrical safety, everybody's thinking, of course, of electric shock, but it's not only electric shock. And this is why it's also very relevant to respect electrical safety rules in low voltage system and 48 volt systems. Of course, the hazard of electric shock is not really given in a 48 volt system, but you still have other hazards, such as electric fault arcing, for example. If you have a short circuit with a battery driving a short circuit current in the range of several kiloamps, then you run easily in a situation where you have an electric fault arc, and that can cause that can cause hazards to people, that can cause hazards to material, and that can even end up in fire or something like that. So there is significant hazards also in 48 volt system, even though you don't need to have trained staff. And of course, it's always about overcurrent, overload, which might also end up in cables or certain components to be too hot to even have the hazard of a fire in the end. So in order to get along with that hazards, there is in electrical engineering, there's very simple basic rules, the so-called 5S, 5 safety rules. I just want to state them here because I think it's still very important also in mobile applications. When you work with electric system, the first thing is to disconnect completely. The second thing is to secure against unwanted, undesired reconnection. The third thing is that verify that the system is de-energized. So not only switch off, but really check if it has been switched off, if there's no unexpected voltage in the system anymore. And then there's two more points. It's carry out grounding and short circuiting. I'll come to that in a minute. And also provide protection against adjacent live parts with covers or barriers. So just to give you an idea of how to do that. So this is again a lab technician and using personal protective equipment in the first place. And in this case, he's just checking the voltage. Here we have a 48 volt system. So we can check the voltage here. And then we're starting this kind of electrical safety rules procedure. The first thing is to switch off. You see the green light is going off. Voltage is switched off. And now we are securing against reconnection. In this case, that means we take off the connector from the battery, the CAN connector. So there's no chance that the battery can reconnect us with the contactors again, securing against reconnection. And the third thing is to really make sure that there is no residual voltage in the system anymore. In this case, again, it's a 48 volt system. So for voltage measurement, we don't really need to have that. We don't really need to have that touch security. But here we can make sure that there is no danger of any short circuits anymore. So just to give an idea with that. So everything is done, and now somebody can start the work. Okay, and just two comments about point 4 and 5. So especially when it comes to mobile systems, you don't really, or you have to really take in, make your mind up if it makes sense to follow rule 4 and 5. For example, grounding and short circuiting doesn't, of course, make any sense when you're talking about a battery system. So you clearly should not short circuit a battery system just to make sure that the rest of your system is not energized anymore. And the same is true for provide protection against adjacent live parts with covers or barriers. Usually when we switch off a vehicle-based electrical system, there is no residual live parts. So rule 1 to 3 is mandatory. Rule 4 and 5 you have to think about thoroughly when it comes to mobile electric system. And this again, think thoroughly is also a really important aspect about training, about staff. There is some certain training system in Germany, and it's unfortunately it is not really the same in every country. Even over Europe, you have different training systems in different countries. Nevertheless, it makes sense to somehow follow the rules. So we have different levels of persons that are allowed to have different ways to work with different ways of electric vehicles. And on the other hand, when it comes to design, there is a certain list of standard. So we have had the question about getting the slides, getting a handout of the presentation. I can answer that question right away. Yes, we will provide a handout of the presentation in the end, just to give an idea of what things we have learned, we are considering there. So I don't want to go through that list step by step here. And again, having an idea of some rules and best practices out of that 5S rules. So just remember, the 5FS rules are coming from an industrial electric world. Nevertheless, at least rule 1, 2, 3 are make very much sense for vehicle electric systems. But in the end, there is some special things to respect. And that's the reason why we created our own checklist for prototypes. I'm just giving an idea of that. So typically you have to fulfill some prerequisites when working in, especially when working in high voltage systems. You always have to have 2 qualified persons in the lab. You have to have some protective measurements. I don't want to go to the details. I'll tell you in a minute why. You have to take some preparation, like for example, cordon off all the work area that nobody is really getting close to high voltage. When you do some commissioning, you have to again follow the 5S rules, switch off, or at least the first 3 of that, switch off, disconnect, secure against reconnection, put on personal protective equipment. You really have to, when it comes to prototypes, thoroughly inspect everything, make tests, and we really have a specification of the tests, and you have to do some measurements. I'm going to give you an idea of that. The first important measurement, of course, is to have a measurement of equipotential bonding. That means that the protective connection between components that could be, in case of an error, could be live parts, should be intact. So here, for example, the guys are checking the connection between every component with an electrically conductive housing and the, in this case, it's kind of the chassis connection of the test stand. And there is a second really important measurement, which is the insulation resistance measurement, where you check that you have insulation both from DC plus and DC minus to chassis again. Because if one of these is not given, then you could have, for example, a chassis connected to DC plus or DC minus, and this could cause a hazard of electric shock, which is quite common, and that's the basic measurements you need to do there. Okay, and then when you really are aware that everything is working well, then you can switch on your prototype system. But as I said, I don't want to go into that in detail. There is a so-called laboratory and prototype checklist that we have been creating, and also this will be shared after that webinar among all the participants, in order to have a kind of an idea what we consider to be best practice in line with all the electrical safety rules when it comes to setting up prototypes, when it comes to setting up test stands, and so on. So this is something we will provide in the end. And just staying at, let's say, at the bottom of the V model, when it comes to setting up electric prototypes, one thing we consider, or we have learned to be very important, is quality control also for prototypes. So there is some aspects that are really important when it comes to, I said it before, for example, here we have a situation where we have a powder coated PDU housing, and we have the cable clamps not really electrically connected to the housing, which caused in the end EMC problems. So usually if you follow best practices like early checks, as I showed before, the equipotential bonding measurement, resistance measurement, insulation tests, and so on, then you can exclude a lot of these EMC problems in the first place. And of course, it's about cable connections. Bad cable connections, avoid that you are leak tight, that you are you bring in moisture or even water into the systems, that you get insulation errors, for example, when it comes to proper use of the shielding and so on, use the right tools. So we think a lot of problems that cause delay in engineering projects could be solved when following the best practice also for prototypes. Of course, everybody has high quality control in production, but when it comes to prototypes, there is a lot of these kind of mistakes that are made in the first place. And we did them all ourselves, so this is something we want to share because we learned about that. So I'm just going through that a bit quicker because I said everything about that, but just to give an example, for example, to provide that for prototypes. We even have these kind of crimping instructions for any kind of crimps that we need to do in prototypes, be it high voltage, be it low voltage crimps. So it shows a step-by-step instruction for every lab engineer, for every lab technician, in order to really make sure that they have the right way to create their cables, to create their connections, and avoid all these kind of problems that I've showed in the slide before. And this really helps us to save debugging. In the end, it's mechanical or it's hardware debugging time in the prototype. And of course, it is a question of having the right documents in place, and probably also without searching, because if the lab engineers need to search the stuff, they won't take it. So it is also about making it easy for the guys. And also here we have went through some learning. So what we're doing here, for example, is really trying to have consistency when it comes to the document. So here we have an example of a electrical design documentation of in this case, it's a service box. And what we do here is we have that electrical design documentation. We do not only have a bill of materials connected to that we see here, but we also have kind of a bill of documents or a document list where we can attach all these kind of documentation, like this crimping documentation and so on, related to every part in that system. So once a lab technician or a lab engineer is setting that up, they have access to all of that document. So there is no excuses for not using that kind of documents. We can do some automatic exports in that and just create a set of documentation that once we work together with customers and projects, we also can provide that right away as a kind of a documentation package. So we see here the document list is attached in the handout, and then you can just open the crimping instruction that we just saw the lab guy working with. So in the end, it's little measures that we learned help us save a lot of time when it comes to prototype setup and especially prototype debugging. Okay, so maybe we can skip that video because we don't need to see how a zip archive is packed and sent to the customers. I think everybody of you know that, but the basic message is having everything in place makes it more easy and reduces sources of mistakes. And from that point, we have been to a lot of points of stations in the V model, and I want to ask Marcus now to come back again because he has some practical summary on how we work with that different and how we bring that into products, how we bring that experience that we just learned into products. So Marcus, the stage is yours again.
Thank you very much. So if we come to our so-called e-kits, that's the name of the product. It's at least a modular kit we prepared to realize complete package solution for customers. And the motivation for this was not so much that I say a product manager had a crazy idea. It was more related an outcome of all what you have seen before, the problems we were running into in system projects with customers, the need that we saw, okay, we run out of resources if we start everything from scratch. So we started to create models on the software side, what Christian, for example, showed, as well as on the hardware side, to get more flexible and faster and moving forward. But we also started then at that point to think this through the whole chain. That means the full scale V model, so that we have, I say, modules we can attach to each other and follow the procedure of the V model. But in that extent that all modules fit to each other because they somehow were less or more tuned to each other. So we save all the verification processes you have to go through in a much quicker way. And that's why we call it the fast lane to electrification or fast lane to zero emission, because it gets much easier to build up this package and evaluate it, not only on the test stand, but also on the machine. In the first step, we thought about, okay, that could be something very nice for smaller OEMs, especially when you have smaller machines, like maybe a small wheel loader to integrate. But then we saw, for instance, that it's also kind of interesting for big OEMs We have some projects ongoing which started with that as a product to sell on the market beginning of the year. And even bigger OEMs come up to us because they were very interested on some dedicated applications where they say, we need something to get out on the market very fast. And because it's not our, I say, number one high runner where we don't have the resources to put on, but have to be out on the market very quick, this is exactly that what we want. So it shows that it's not only made for this small, I say, compact equipment like what you see here with this excavator or maybe a small wheel loader. It also can be the base for bigger machines on auxiliary functions or maybe on the main functions, like what we have ongoing at the moment quite a lot is that we have, for example, bodybuilders, that means truck applications, where you have, I say, the unit for the implements as a separate unit attached to the truck chassis, and where, for example, the OEMs come up and say, hey, we want a solution where we can drive with the truck like it is to the construction site, and on top we have, I say, electrified drive system, where we then can operate, for example, the implement functions on construction site fully electrically. But we need it that it works quite quick. That means we are on the market just in time, and we do not want to develop the whole package by ourselves. The importance here is that we do not want to sell a black box. That means we need to have a certain open dialogue and also open architecture, so that the customer, especially the bigger ones, they want to understand what's going on, that they see what's going on, and we also are kind of flexible with the modules in between. I think this is a little bit mixed up, or yeah. So what we have here is coming back to the picture what we just discussed before. I see there still are things going on. On the first session where I asked, for example, what is the most or highest importance for you? And what you can see here on one side is efficiency, but on the other side, a very important point is scalability, easy integration, needs to fit in the existing framework, minimum technical risk and effort, short realization time, and scalability. So these are things we implemented into the E-kits. And therefore we have, I think a quite good base to come closer to that what we discussed in the first session. So I think this is something which really helps you to get faster there. And like I mentioned before, it's not a closed kit, it's really scalable. So you can use it as a base for maybe building up, bigger systems or side functions in the application. In basic, the heart of the system is what Christian already showed before, the PDU, where we less or more make the complete distribution to all the individual components in the system. Then we have, of course, the drive for the pumps. You can have the system, of course, with the pumps directly integrated. Actually, we talk about air-cooled systems in a power range maybe up to 20 kilowatts. It can be a little bit higher or lower. It really depends on the applications. Like we have some customers, they go of course higher, but it is very much related, for instance, to the load cycles. But it gives you very flexible standards, and also, for example, on the battery packages on our Leo systems from Invenox, we are kind of flexible, so we can start, for example, on a very simple application, maybe with one package, but you easily can upgrade this from the 6 kilowatt hours to 24 kilowatt hours. And this gives a certain flexibility on the application, and especially is very helpful in a practical way if you have a customer who does not really know too much how are the load conditions and load cycles on his machine, and needs a certain flexibility, because it's easier with this package to add, additional battery package or take it away if we see, okay, it maybe was a little bit too much, and everybody knows how expensive batteries are. And another very important point and a goal getter on this project or product is that we also integrated the whole charging architecture, so that makes it quite easier for the customer to build up the whole package with, individual and several different ways how to charge the system, but also, for example, how to attach, for example, then the vehicle to charge it. If we now come to the point of the view of the OEMs, of course, very often the questions come up, if you sell a package as a complete package, how do I differentiate myself if I use a standard package? Because everybody, like also my competitor, can buy the same package. Yeah, he's maybe correct on that side, but to be honest, if you look a step further, for example, or back in the diesel times, how was it with the diesel engine? In basic, it's a similar situation. A lot of OEMs are using the same diesel and nobody's discussing about, oh, what is our competitor doing? So it's accepted there, and I think this is also something you have to discuss if you go on the electrical side, because if you develop everything individual by yourself and every time an individual solution, it will consume resources, it will generate costs, and you will get maybe a system which is not so easy to maintain. So it's more the question, you maybe really have to look back in the diesel times, where are the spots and where are the points where we do the, I say, differentiation in the machine or in your product, and very often if you look deeper in, you will find, okay, it's somewhere in a complete different corner. So it's maybe the machine productivity, the overall vehicle architecture, or the control functionality, or how the machine behaves in the controllability, the parameterization and fine-tuning, efficiency in the hydraulic system, and things like that. Or integrate other smart functions you do not have, or maybe some features even in the A-kit others do not have. And these are things which I think, or we think, are much more interesting. And when you look on the diesel, you can exactly see this, that the diesel maybe is used at different OEMs on doing the same application with the same requirements, but there is no discussion, okay, I do not want to have my competitor to have the same. So I think this is a thing we also have to overthink and change a little bit in the mindset, because otherwise we will be not on the market, also on the OEM side, in time and fulfill the requirements what our environment, but also I say the regulations will ask us for in the future. If we now come to the overall, it's a big question for how to overcome the requirements. Here's another picture of the V model. We have to go through, and we pointed out like a run over hurdles, and we will help you to handle these hurdles, be faster on the market, save costs in the development, have a flexible solution. And the other thing, of course, is if you are faster on the market, you maybe save also money on taxes. You maybe have to bring out or the customer, for instance, your customers, with their fleets on the market, because they get, I say, a payback from the government earlier than, for example, if you maybe march forward the conventional way. And as an adder, for example, what we do here on the 48 volt side, we talked a lot about higher voltage levels before we have in development, where we have products, I say, in the market. And of course, we do the same, for example, for the high voltage side, and are actually in the process to develop an 800 volt kit. And if somebody is interested and close by, you can show up next week at the IFAD Municipal Fair in Munich, which is, I say, the #1 in the world. And there you can see, for example, a display of our 800 volt kit. So to close this session, I want to just ask an argument, for example, or 3 arguments better. What are, for example, major arguments which would put you in the situation if you would be asked, okay, do you look for a certain standard and what should be the content of that standard? So I again ask all our important customers to maybe write down what are the 3 major arguments you see, for example, for your own purpose, for your application, what is really relevant. If you would say, I need some sort of standard modules or complete kits in your application. I see, the timing takes a little longer than
it's not just
voting.
A question,
yeah.
It's an open typing question, so let's give the people time to really bring their answer.
plug and place, nice.
But also things like reliability.
Yep.
That's often things you do not hear in the very first discussions of a project, but from a lot of people who have made bad experience with non-reliable products, with products switching off all the time in every situation and things like that. So reliability, I think, when talking about the next, let's say the second and the third generation of electric machines, will become more and more relevant to the machines, also for end customer acceptance. Because it's not the early adopters only anymore, but it's really, we want to achieve the whole market. So availability will be key.
Yeah, that's a big point we really see in the applications. Very often the questions are not risen, how do I handle service and things like that. And that of course is also related to reliability, because if you don't have a reliable product, you will waste all your money on service. And warranty claims. So that is a very important point for us. Fast on the market, with security, correct. I think that's what we also can see. You find solutions similar on the market, but then it's something which works, but then certain things, especially if it comes to safety, are not taken under consideration. And I think that is a very crucial point. Okay, I think there are not too many writing anymore. Yeah, I can see that a lot of the questions are similar, or the answers, and fit a little bit in also our view. There are a few new things, but I think it's very much what we had in scope when we developed this, and thank you for that. And I think we can come to the final now, so I will give it to Christian.
Thank you, Marcus. So we're approaching the end of the webinar, so let's try to summarize what we have seen today. So this is what we started with. We want to have some interesting practical tips, bringing theory into practice, and we did that along the V model during this presentation. And some of the things, just some of them summarizes as a summary, is we talked about iterative component sizing, about pragmatic approaches, about using early system prototypes to have early learning and early possibilities to correct. Use that for testing. And of course, it is about modularization and standardization. Just to remember again, we are off-highway. We have to find some economies of scale, not on an enterprise or not on a single company basis, but on a market basis. And that's why we need to work together in that kind of modularization and standardization. So actually, it's not turning theory into practice along the V model, but also along the hype cycle, to just close the gap to what we showed in the beginning, because we all want the same. We want to achieve that point here. We have come across that point. That was a very nice time. But now we have to go there to really achieve a broad market acceptance. And this, I think, is working together, having these learnings together, is things that help us all together. But in the end, it will be about customer acceptance, it will be about cost, and it will be about modularization and standardization in the market. So we have to somehow find the fast lane to come there, because nobody's really having fun in that part. So we should do our best to come as soon as possible to here. And this is what we want to be part of. This is what we want to help with, what we want to share our experience, but also gather further experience. So we love to discuss that with you in projects, in discussion, in common workshops, discussions, and so on. But nevertheless, we also have some room to do that here. So we have a Q&A section open from the beginning of this webinar. So there is some questions that have been there. And of course, you still have the possibility to ask further questions. So I'm just going into answering some of the questions right away. So, for example, starting with the first one, is the motor calculation tool free available? So, for the time being, the motor calculation tool is a tool that has been designed from the engineers for the engineers. So we are about to roll to a rollout process from step by step. But for the time being, at the moment, it's only available to technical salespeople inside HYDAC, and it will be rolled out there and tested, because also here, it's about testing. It needs to be robust before giving it out to the world. And in the long run, yes, it will be available, but unfortunately not as of today. The second question is maybe really something that is closely connected to the fourth, or now it's the third question, the 500 amps rule. Here we have an example, is for example 48 volt 1000 amps. Does it not also make sense for a parallel operation? So that means that you have several components in parallel, or several, let's say, cables, or even several inverters that all can carry the 500 amps, but in the end you will have a system voltage of more, you have a system current that is more than 500 amps. That might of course make sense in certain applications, and I also want to emphasize here that the 500 amps rules is more a rule of thumb, of course, and there is application where it makes sense. So I don't want to say it does not make sense to have more than 500 amps in general, but in every case when we cross that 500 amps rules, at least we take a closer look. Does it make sense, or is there a more cost-efficient solution? Because just the prices are increasing. And if you parallel, for example, several drives and each of them has 500 amps continuous, you need to get the 500 amps continuous somewhere, and you need to get all of that out of the PDU. So probably on the PDU inlet, you might have 1000 amps or 1500 amps or something like that, and that is again driving cost. So I think it's a good rule of thumb, but you need to look into detail step by step. So here again, here also we have a question about the regulations. So for example, here it is about the ECE R10 regulation. Do you conform at system level or at component level? So usually conforming ECE R10 at system level makes sense as kind of a pre-compliance test, because in the end the vehicle has to follow the certification, the ECE certification. So the only thing we can do is have a pre-compliance certification. So we're doing pre-compliance testing, and we're trying to have that on subsystem level, but in the end it doesn't really release the vehicle builder, the end, or the OEM to do that certification testing for the vehicle. It's just reducing the risk during the course of development there. And another question we see here at the top is the question about the rules for the training of the staff in China. That's a question, unfortunately, I cannot really answer. That's a problem I mentioned when it comes to the rules. We have some very clear rules in Germany, and we see that we have similar rules in countries close by, but even they might differ in some details. So it's really a mess when it comes to training of staff, that today we do not really have standardized rules. So what we are offering, what we have been offering, for example, to our people, also to our foreign people, is to have an English version of the German high voltage training with the German certification that at least gives you all the best practices, gives you a certificate that you have been learning all that. But we still, of course, cannot guarantee that it is accepted from authorities in different countries. So this is something that has to be taken into account country by country. But I think it also makes sense, if you're interested in that, contact your local HYDAC guy, and they can contact us, and we can maybe find a solution together. Okay, I don't have seen any further questions coming in. So Marcus, would you just come back again?
Yeah.
So we'd like to thank you. We'd like to thank for your participation. We'd like to thank you especially for giving your feedback in Slidos, bringing in your questions. We really enjoyed being here. We really enjoyed sharing experience, and we hope that we can, by doing this, trigger some further discussions where we not only can share experience, but also gain experience again. Because remember the Dunning-Kruger curve, none of us, I think, should be considered themselves as an expert, but we're all learning on the way to become an expert sometime. So, and that's something we want to do all together with you. So, and also to keep that alive, we will have follow-up events like this webinar. There will be further webinars, so we will send out information during the course of the next week regarding the handout of the presentation today, regarding the results of the Slido polls, also handing out the lab checklist for electrical safety, which we consider for us to be a good practice, and maybe one or the other can really make use out of that. And we will also inform you how to follow up with the next step in this forum e-mobility. So thanks a lot. Again, from my point of view, it was really a pleasure to have this webinar, to share experience, and thank you again for participating.
Yeah, I can say the same from my side. It was some work to do, but it was 10 times worth it because it was fun to follow this up. And I think if you have this interaction, especially via Slido, and get certain feedback, I think that is really a good interactive way how to communicate. And like I just offered before, and Christian, take the chance to visit our next webinars, or like next week when I will be on the fair almost the whole week. Christian will be there, so we are there for live talk and also show the products and so on. So use this chance, or if you have any questions, don't hesitate to contact us directly or via our colleagues. Thank you.
Okay, thank you very much. And remember, we're here to help, we're here to discuss, and we would love to help each other to come further in the hype cycle of electrification. Thank you.
Thank you.